My name is Matthew Hall, and this is lab number 4 about oscillations. Now, the purpose of this lab is to graphically and mathematically model the relationship between an oscillating mass system and the conservation of energy. This lab included many physics concepts that we have discussed this year, including Newton's second law, which will explain the differences in the various forces that are acting on the system, such as spring force and the force of gravity, different oscillation equations, as we'll see in the code, and then the conservation of energy, which includes kinetic energy, potential energy, spring potential energy, and the total combination of all these energies. And altogether, we'll see that energy is conserved in the computational model. Now, according to the observations, we see a difference in the tracker model and the computational model. In the tracker model, the oscillation begins at a angle from the vertical, which means that towards the end, the energy is not completely conserved, and because this is a realistic scenario, we'll see a tail in the amplitude, as you can see in the top right corner of the screen. The tracker data it appears to lose energy towards the end, but in the computational model, you see that the green and red lines, which demonstrate the kinetic and potential energy, they don't seem to change in amplitude by too much of a variety. All this does is this just shows that the conservation of energy can be predicted, but it won't exactly resemble a observed model. For my specific data, I got a time period of 1.619 seconds, which can be shown in the graph. A spring constant of 6.05 newtons per meter, which could be obtained by calculating oscillation period and relating that to the spring. And then the initial length of the spring is 0.049 meters, and that's found by using Newton's third law. According to the code, there's a lot of things that had changed, and there's the addition of energy and various forces. For instance, we had to change the mass of the system to accommodate the mass of the spring, or the mass attached to the spring, in which now is affected by gravity, and that's why gravity is included in the net force. Additionally, the spring constant was calculated, and the L naught was calculated, and that will change the predicted model and how the graph is displayed. Also, you can see the kinetic energy, potential energy, and spring potential energy formulas found in the code. Also, there's the initial components, which are found because of the fact that we were given initially the distance of the tracker model of 0.7 meters, but there's a bit of a deviation between the spring and the mass of the spring, the center of the mass, and from where we found 0.7 meters. So in conclusion, we can successfully say that the energy principle has been satisfied, and that is best found in the model. So if you refer to the graph, because of the idea that the amplitude of the red and the green lines stay relatively constant throughout the time period, it shows that the conservation of energy is truly there. No energy is lost to the system as far as the predicted model is concerned, and everything is contained within the constraints of the spring and the mass and the Earth. However, you can see that energy is not exactly conserved in the observed model, and again, that's a lot attributed to the fact that it was dropped at an angle, and it's more of a realistic scenario in which eventually the pendulum in the spring would have to stop moving. Also, so there are components of the period of the oscillation, but however, those in a realistic scenario, they won't stay constant, but in a computational scenario, they will stay constant. So what I mean by that is, so this pendulum, it obviously acts in an X and a Y direction. It's not dropped vertically or horizontally. So there will be X and Y components. However, even though, so you can see the trajectory it changes throughout. All that does is that just changes the direction of the oscillation periods, but it shouldn't change the amount of time. It really depends on where you've designated your X and Y positions.